Hi guys, this is Mrs. Foy, and this is a screencast on calculating molar mass or formula mass, and then how to use that in a conversion of either the number of particles to a mole, or the number of grams to a mole, or the number of particles to grams or grams to particles. So before we get started in how to calculate molar mass, I just want to show you this thing called a mole map. And some chemistry teachers like to use this because it gives you a visualization of what some of these problems are. So for example, if you were given a problem that said, hey, you have, 5 times 10 to the 23 atoms of copper, how many moles is that? Then you would use your factor labeling skills, your conversion skills, using Avogadro's number. 1 mole is equal to 6.02 times 10 to the 23, and then you use that to convert the number of particles to moles. And we have done this before in my class, so this is a review for that. What's new for my students at this point is now I am giving you the mass of either compounds or elements, and I'm asking you to find how many moles in it. So in order to do that, you have to do something called finding the formula mass or the molar mass, which I'll show you in just a second. But the last thing I wanted to tell you is that now you are going to be able to do 2-step factor labeling problems. So for example, if you are in the number of particles, if you're given the number of particles or atoms or molecules, formula units is just what we call a particle that is an ionic compound. But if you have the number of those and then you want to convert it to moles, you use 6.02 times 10 to the 23 is equal to 1 mole, and you set up your factor labeling or your conversion so that your units cancel. And then if you're in moles and you want to get to number of grams, then you use the formula mass, which I'll show you in a second. But now you're going to be able to do 2-step problems. So if I give you number of particles, you have to convert to moles first and then grams. If I give you the mass of a compound and I say how many particles, you have to convert to moles first and then go to atoms or molecules. So that's what we call a 2-step. Okay, so let's talk real quickly about what is the molar mass. So the molar mass is sometimes called the formula mass. It is just the mass of 1 mole of that substance. So let's take water, the easiest thing we know, right? So the formula for water is H2O. And I see that I have 1 oxygen and 2 hydrogens. And so these numbers here, guys, are from the periodic table, right? You've got your handy-dandy periodic table with you, and I can look up oxygen on the periodic table, and I see it's 15.994 grams per mole. If I was just measuring the mass of 1 atom of oxygen, it would be 15.994 AMUs. But a whole mole of it, 6.02 times 10 to the 23 particles, is going to weigh 15.994 grams. And then hydrogen, I look up hydrogen up here, and its atomic mass is 1.00794. A mass of the average hydrogen atom is 1.00794 AMUs. But because we have a whole mole of it, we now use grams. So I have 2 hydrogens per mole of, or per molecule of H2O, and so that's why I have this on here twice. So I add those up, and if your teacher asks for this many sig figs, then the molar mass of water would be 18.0153 grams per mole, or however you are supposed to round that. That could be the formula mass of water or the molar mass of water. Okay, so here's another example. What is the molar mass of sodium chloride? So in my class, you have to know how to write the formula. This is something called nomenclature. So sodium chloride I would write as NaCl because I know that everybody in this column right here has a +1 charge when they form an ion, and I know that everybody in the halogens is going to be a -1. So that's why it's +1 -1. I have several screencasts for nomenclature. If you're confused, you can search on YouTube for that. But anyway, 1 mole of sodium is 22.989770. That is what I look at when I look at the atomic mass of sodium, and my students are going to round that to 1/10 of a gram. And 1 mole of chlorine, when I look here in chlorine, I see that the mass on the periodic table is 35.4527 grams, and I'm going to round that to 35.5 grams. And so because I have an atom of each in that compound, the molar mass of sodium chloride would be 58.5 grams, or 58.5 grams per mole. All right, great. Let's use that to do some problems. Okay, so sorry I did this problem in class, and I wanted to show you how to do it here. So I already did a lot of this writing, so excuse my messy writing here. So let's just look at one problem per time so we don't get all confused. Okay, so the first problem was, what is the molar mass of sodium oxide? Sodium oxide. So in order to write that, you had to know the charge of sodium was +1 and the charge of oxide was -2. And so the formula for sodium oxide is Na2O, because I have to have 2 of the +1s to balance out the -2. So then I look on my periodic table and I see that the atomic mass of sodium is rounded to 23.0 grams. I have 2 of those, so times 2. And the atomic mass of oxygen is 16.0 grams, because this is a mole of it. I'm using grams, not AMUs. And so the molar mass or formula mass of sodium oxide is 62.0 grams. Pretty easy, right? Okay, so now another problem I can ask you is, if you have this many particles, if you have this many, technically it would be a formula unit, but you can call them molecules for now, of sodium oxide, how many moles would that be? All right, so this is going to be example of going from, let me go back here for a second. This would be example of going from the number of particles to moles. So this is just a single step mole conversion. So I write down what I'm given, 2.75 times 10 to the 25 particles of sodium oxide. Oh shoot, I forgot, wrote that wrong. Let me fix that right now. Make a little 2 here. Sometimes when I get going so fast, I forget that. Awesome, awesome, thank you. Okay, so anyway, I write down what I'm given. Here's my Avogadro's number, 6.02 times 10 to the 23 particles in a mole. And I just use my factor labeling skills to put the Avogadro's number on the bottom so the particles cancel. And I have 1 mole. I do the math. I subtract my exponents, because that's what I do when I divide. I have to move the exponent to get it into scientific notation. And then because I have 3 sig figs here, I have to have 3 sig figs in my answer. And so I round it to 4.57 times 10 to the 1 moles of sodium oxide. All right, great. Let's try another problem. So this problem is, what is the mass of 9.75 times 10 to the 24 atoms of lead? All right, so let's go to back to my mole map for a minute and just kind of see what I'm asking you to do here. So I have numbers of atoms of lead, and I'm asking for how much they weigh. So I'm going to have to do a 2-step conversion problem here. I have to get to moles first, and then I have to go to grams. So here's how I'm going to do that. I write down what I'm given in the problem. That's what you do first. 9.75 times 10 to the 24 atoms of lead. Here's Avogadro's number that I'm using with my atoms on the bottom to cancel those out, equals 1 mole. And then 207.2 grams, that's how much 1 mole of lead is. And you might say, well, how did you get that, Mrs. Foy? Well, I looked on my periodic table and I found lead. And lead's atomic mass is 207.2. Because it's a whole mole of it, I'm going to use 207.2 grams. So this is what we call the molar mass, the mass of 1 mole of lead. So I write it this way so that my moles cancel. And now I have my beautiful factor labeling problem where I just have grams set up. My atoms cancel, my moles cancel, and now I just multiply across. I subtract my exponents because I'm dividing those exponents, and then I divide by 6.02. So it's 9.75 times 207.2 divided by 6.02, and that's how I get this 335.5. The 10 to the 1 came from me subtracting 10 to the 24 minus 10 to the 23. So now I have to get it in correct scientific notation, so I move that decimal over, make this number smaller, have to make that exponent bigger. I look over here at my original problem, which I have 3 sig figs, so I have to round to 3 sig figs, and I have 3.36 times 10 to the 3 grams of lead. That is how much that many atoms of lead weigh. Okay, so now I'm just going to do kind of the opposite problem. Here, I am given the mass of this compound. I have 65 grams of iron 4 oxide, and the question is, how many particles of that? How many molecules is that? So going back to my mole map, I am given 65 grams of the compound here, and I asked how many molecules, technically formula units, but we'll say it molecules, is that. So I'm going to have to convert first to moles, and then again I'm going to convert to the number of particles using Avogadro's number. So that's exactly what I'm going to do here. 65.5 grams of iron 4 oxide in 1 mole. Now I got to figure out how much does 1 mole of iron 4 oxide weigh. So this is where I have to use my nomenclature. Okay, so iron 4, I know that the Roman numeral means the charge of a transition metal, so iron 4 is Fe plus 4. Oxide is O minus 2, I know that because every one in oxygen's column is a minus 2 and it forms an ion. And so that's how I get the formula FeO2. That is the formula for iron 4 oxide. So the mass of iron is 55.8. I found that from looking up iron on the periodic table. And I only have one of those. And oxygen atomic mass is 16.0. Found that on the periodic table. And I have 2 of them because I had to write my formula so my charges balance. I have 2 of those. So I add that up and I get 87.8 grams. That is the molar mass of iron 4 oxide, or the formula mass. So I set it up this way so that the grams are on the bottom so that they're going to cancel. 1 mole of iron 4 oxide weighs 87.8 grams. So my grams cancel, and now I'm at moles. But I don't want to stop at moles. I need to go all the way to the number of particles. So then I do one more conversion. 1 mole is equal to 6.02 times 10 to the 23 molecules. Good old Avogadro's number. My moles cancel, and I'm going to end up with molecules. So if you want to pause the video just for a second to see what you get with this, that would be great. So pause it just for a second. Okay, and the answer is, when you do that, 4.5 times 10 to the 23 molecules of FeO2. Remember, there's just 2 sig figs because that's the original in my problem. So I hope that's been helpful, and I'll see you in class.